So my name's Sean Connolly. I'm a professor of marine biology. I work at the College of Science and Engineering at James Cook University and also in the ARC Center of Excellence for Coral Reef Studies. I'm not sure I could pinpoint one reason why I decided to become a scientist, but I like solving hard problems. And I've always been interested in nature and particularly in how ecosystems are put together and how they've evolved over time. Mostly I'm interested in questions that have to do with marine biodiversity. That is, why are there some more species in some places than others? Why do certain species live in some places and others live in other places? Why are some species more abundant in some places than others? And of course those kinds of questions have taken on a new urgency because with the Earth's climate changing and other types of human impacts on the reef, then for coral reefs, for example, we need to be able to anticipate how reef ecosystems are going to change under different types of scenarios of what we do in the future and consequently what happens to the climate in the future. So if we want to try to paint a picture of what the reef looks like if we take one path into the future compared to another path, we need to have a good understanding of how species interact with each other and how they respond to their environment. So in my research, I use a combination of laboratory experiments, observations made in the field, and mathematical models. And so you might wonder how we would use mathematics to understand nature, but if you think about nature, nature has got many dimensions. If you look at an ecosystem, you have lots of different species that can all be abundant or rare, that all change over time, and those systems are very dynamic. And so to understand how a system that's very multidimensional, that has lots of elements to it, and a system that changes a lot over time, then you almost always employ mathematics, whether you're doing biology, whether you're doing chemistry, whether you're doing physics, whether you're modeling plate tectonics and geology. And so we use math as a tool, a way to construct models of how nature works. And one of the great things about using mathematics is that we can construct a model of a system. We can ask questions about how that system would respond in the future. We can do experiments on that system, if you like, on that model. And we can say, okay, if we change the system in this way, if we change how the system works by altering global temperatures, how does the dynamics of the system respond? I got really interested in combining mathematical modeling with fieldwork really very early on. My first year as an undergraduate, when I worked in a research station in the Luquillo experimental forest in Puerto Rico, and there was a group of scientists that were developing a food web for the Luquillo experimental forest, and they were using mathematical models of the food web network as part of that process. And in hearing them give seminars about the work that they were doing, I realized that if I wanted to ask the kinds of questions about ecological systems, about how they're going to respond at large scales and over long time frames, then I needed to get on top of those techniques. Otherwise, the field was going to leave me behind. And so I went back to university after that summer, and I decided to combine the biology I was studying with mathematics coursework.